Okay, so in this video, we'll work through some of these mechanism problems from the workbook. Let's take a look at these. So our first one, this is on page 101. Our first one is we have a chiral molecule. It looks like we're starting out with something that is enantiomerically pure. And then we're subjecting that to sulfuric acid in water. And what we're getting out, these little rings. And you'll note that the rings are not enantiomerically pure. And that is telling about what the mechanism is. So usually, with the exception of last chapter, when you're asked to draw a mechanism, you're given the products. And that can give you a clue about what the mechanism actually is. So if you're running a reaction in the lab, you're only worried about the mechanism of it usually after you've run it. So you can look at your product and say, oh, this is what I've got. Let's try and puzzle out what the mechanism is here. And what I can see from this is a racemic mixture. And to me, that implies that this probably went through some sort of achiral intermediate, or most definitely did. And the other thing, and this is probably less obvious to you, is that this, let's number this. So we've got 1, 2, 3, 4. And I'm going to number the sulfur as well, even though I typically leave the heteroatoms out. We're going to call that 5. And so you'll notice that we've got sulfurs there. The sulfur is bonded into what appears to be carbon 1. So you'll note carbon 1 has a methyl group attached to it. Carbon 1 has this methyl group attached to it. And the sulfur is biting onto carbon 1. That seems clear. So carbon 1 is here. Yeah, so carbon 1 is that, and then we've got 2, 3, 4, and 5. So this looks like an intramolecular substitution reaction. You'll note that the hydroxyl group, which is there, is gone when we get to the products. There is no alcohol functional group in the products, and it's been substituted for by the sulfur. So originally that carbon 1, this carbon 1 here, that I've highlighted in green, was bonded to an oxygen. Now that oxygen carbon bond has been replaced by a sulfur carbon bond. And the weird thing here is that the sulfur is connected back into the molecule. But as you'll see, hopefully, when I draw out the mechanism here, if you couldn't get it on your own, is that it's not that much different than stuff that we've learned already, even though it looks kind of wonky. Okay, so it's a substitution reaction, which means that it's nucleophilic substitution. The nucleophile is actually inside the molecule. And then the fact that it's racemic, which is the first thing that I looked at, since this is racemic over here, that tells me that this is probably going to be SN1. Because if it was SN2, we would see clean inversion. But since it's not inversion of stereochemistry, and we do end up with a racemate, racemic mixture, we know that it probably is not going to be SN2, it's going to be SN1. All right, so I'm in acid. I've got an alcohol. What's going to be my first step here? It's going to be to protonate that. And that converts this from a bad leaving group into a good leaving group, which sets it up for whatever type of nucleophilic substitution I'm going to do. And so if this was SN2, I would have my nucleophile attacking at this point, but because it's racemic, I know it's SN1. And so what I'm going to draw here is this coming off. And this shows us where we've lost our chirality. So now, what was once a chiral center is now just an sp2, which let's see, so this carbon, right? That was our chiral center. And now, in this next step, we see that it's just an sp2 hybridized, or approximately sp2 hybridized carbocation. I'll draw the hydrogen coming out the back here. Now we see that that hydrogen is just hanging out and everything is planar. All right, so then this is the part that's sort of fresh. So then that part of the molecule can now come in and do, that part of the molecule, the nucleophilic part, come in and do nucleophilic attack on the carbocation. So you note I moved my positive charge because I wanted to show that the electrons from the sulfur are actually connecting into the carbon atom. They're not attacking the positive charge. That's a really common mistake. So if that's the way you've been drawing it in your notes, make sure that you correct that. But so if it attacks from the top, let's see, if it attacks from the top, I'll get one isomer. And if it attacks from the bottom, I'll get the other isomer. So I'm not going to draw that out explicitly. You're welcome to play around with that if you want. But yeah, so what I would end up getting in the last step is, oh, wait. Not the very last step, sorry. So I'll draw one of the enantiomers here. So you'll note that after it attacks, I still have a proton attached there. And so my final step is really deprotonating that. So water comes in, steals that proton. And those electrons go back onto the sulfur. And now I finally have my product. And then, we also get the other enantiomer because that's what you would get from attack on the other face. And so what you've got here is an intramolecular SN1 mechanism. So it looks radical, looks not radical and radical in the sense of different, but it's actually something you're familiar with. The tricky thing is kind of getting everything drawn into a ring. If you're confused about how to go from this part to actually having the ring, one thing you can do is just go in and number everything. 5, 4, 3, 2, 1. And then you can just come down and draw out a pentagon since you know it's going to be a 5-membered ring. And then you can go in and just arbitrarily start somewhere. So 5, and then we could say 4, 3, 2, 1. And then we can look at the 1 position that I've highlighted over here in green. So if we look at the 1 position there, you see it has a methyl group and a hydrogen coming off of it. And so I want to add that in. And what enantiomer I get at this step, I haven't explicitly shown anything in 3 dimensions here, so I just kind of draw 1. It doesn't really matter which one you draw. And then I just say plus enantiomer, or you draw out the other enantiomer, whatever the problem is asking for. So I like that mechanism. All right, let's look at this other one. This one looks a little bit more grueling. All right, so in this one I take sulfuric acid and I take isopropanol and I mix those in. What am I getting here? And somehow I'm getting the substitution of the alcohol for the isopropanol. And so I'm adding isopropoxide or whatever to the molecule. The weird thing to me is that, that's the carbon you would expect substitution to go on. but in fact, it's on this carbon, which implies that there's some sort of rearrangement, and somehow that rearrangement allows the ring to stay intact. Let's take a look at this then. So I'm not totally sure just from looking at this what happened. I'm just going to start drawing out what logically should happen. I'm assuming this is an SN1 reaction, since we're seeing rearrangement. And it's a secondary carbon, which alcohols typically go through SN1 for secondary. Okay, so in the first step, if you're in acid and you have an alcohol, you almost invariably protonate it. So far I'm just going through your standard alcohol in an SN1 reaction. That pops off and gives me a carbocation. This must be when things start to get weird. Hopefully we can figure out what's going on here. Okay, I've got a positive charge there. Somehow the isopropanol rather, is adding to the middle. So I guess what must have happened is there's a hydrogen there. Okay, so my rationale here, just to be clear, is I'm looking at the product. Okay, so the thing that differentiates this from like a synthesis problem is, in a synthesis problem, I'm given the product and I'm trying to like push through a whole bunch of reactions to get there. In this case, I'm kind of told how the reaction is going to go, and I'm using that to figure out the most reasonable way that we could get from the reactants to the products. Okay, so this isn't like this is a little bit different in that I know ultimately, I guess what I'm saying, I know ultimately that this isopropoxide group must attach to this carbon atom, even though that's not immediately clear to me when I look at the problem. But now that I'm kind of going through it, it becomes a little bit more clear. This carbon is secondary, and the carbon that is next to it here, that carbon is tertiary. And so we have the potential for a rearrangement that will lower the energy of the carbocation conceivably. And this one goes through a hydride shift. So the electrons that are inside of the hydrogen-carbon bond go with the hydrogen and form the new bond next to it. So this one already has a hydrogen. Right? Now it's got two hydrogens. So those electrons go with that hydrogen. And now this carbon is down a hydrogen, right? So it's picked up a positive charge. It lost those two electrons, and so it's hypovalent. Now we can see where the isopropanol comes in at. So now I've got the carbocation there. This thing's nucleophilic. Bing, it goes in, attacks that positive carbon. Don't know how easily this reaction would go in real life, but it looks reasonable enough on paper. Okay. And then finally in the last step, water or something comes in and just pulls that proton off. So again, you know, at first glance, and this one I felt more intimidated by than the last one. At first glance, it's like, I have no idea what the hell's going on. But if you assume that the question is fair, which is usually, I mean, especially for you guys on a quiz or something, you can assume the question is fair. We're not intentionally trying to trick you. Then you can assume that whatever fundamental things we understand should hold true. And so I just started pushing through an SN1 mechanism, and then as soon as I formed the carbocation in this step, I was like, oh, okay, that makes sense. We get a rearrangement, and then it just attacks the tertiary carbon. And that's what you get. That's how that mechanism works.